In the early months of World War II, before America fully understood the storm it had entered, a rumor began circulating through the corridors of power in Washington. A rumor about a Japanese fighter plane so impossibly agile, so unnaturally precise, that it defied every calculation Western engineers believed about flight. Pilots whispered it, commanders questioned it, engineers denied it. The stories coming out of the Pacific sounded like exaggerations, like myths carried by terrified air crews pushed into a war their nation had not wanted nor expected. But the myths were real. Japan had created a fighter the Americans did not know how to beat, and buried within its wings was a curve, a precise, delicate, mathematically perfect shape, invisible at a glance, yet powerful enough to change the air itself. A curve America would try to copy. A curve America thought it understood. A curve that would humiliate American engineers, cost countless lives, and expose a brutal truth about aviation physics. Some shapes cannot simply be copied, they must be understood. This is the story of the Zero, the fighter the United States underestimated, dismantled, copied, and still could not replicate, and the wing curve America missed. A ghost in the Pacific. When the war began, American pilots expected the Japanese to field second-rate equipment, machines outdated, inferior, or improvised. That belief didn't just come from arrogance. It came from decades of intelligence failures. American analysts believed Japan could manufacture weapons, but surely not advance them, surely not innovate, surely not surpass the West. But then came the reports. Reports of American fighters, Wildcats and Buffaloes shredded in seconds by a Japanese aircraft no one had predicted. Reports of dogfights that lasted less than a minute. Reports of pilots who said they didn't see the enemy until it was too late, because the enemy was already behind them. The United States had entered the sky over the Pacific expecting an easy fight. Instead, they met the A6M Zero, a fighter with impossible range, impossible maneuverability, impossible climb rate, impossible agility. Impossible because American engineers believed it could not exist. The airplane that should not fly. Before Pearl Harbor, American intelligence dismissed the Zero as propaganda. No airplane could fly that far, turn that tightly, and still carry weapons. The numbers didn't add up. Unless someone had solved a problem Western aerodynamics had been stuck on for years. The problem was simple to describe. How do you make a wing that cuts through the air at high speed, but also lets you turn tightly at low speed, without losing structural strength? Every nation had pursued this balance. Every nation had failed. Except one. Japan. And the secret lay in the shape of the Zero's wing. Not the size, not the aspect ratio, not even the slender profile, but the curve. A single, continuous, flowing curve, one that produced lift at angles American engineers believed were impossible. A curve carved from traditional Japanese woodworking philosophy, refined through wind tunnel data, and then handcrafted with terrifying precision. The Zero did not fly like Western fighters. It flew beyond them. America panicked. By early 1942, American pilots were being outmaneuvered at every altitude. The Zero's agility allowed it to climb past opponents, outrun opponents, outturn opponents, and then strike before an American pilot could even react. What the US desperately needed was a Zero. Not a captured fragment, not crashed debris, a fully intact aircraft. Only then could American engineers figure out how Japan had achieved its aerodynamic miracle. Only then could America copy it. And then, in June of 1942, the impossible happened. A Zero fell into America's lap. Not destroyed, not burned, not torn apart. Intact. A perfect trophy. The American engineering community rejoiced. They would study it, they would replicate it, they would master it. Or so they believed. The Zero that survived. The miracle Zero came from an unlikely place, the Aleutian Islands, far from the warm waters of the Pacific battlefield. A Zero pilot, after engine trouble, attempted an emergency landing on the remote island of Akutan. His landing gear dug into soft soil. The aircraft flipped. The pilot died instantly. But the aircraft, it remained nearly perfect. When American forces found it, they could barely believe their luck. For the first time, the United States had access to the enemy's deadliest weapon, untouched. American engineers celebrated. Finally, they could uncover Japan's secrets. Finally, they could copy the Zero. But what they found inside would humiliate them, because copying was not the hard part. Understanding was. The dissection. When the Zero was brought to North America, engineers from every branch of the military and multiple manufacturers, Boeing, Grumman, Vought, swarmed to inspect it. They expected crude Japanese construction. They found craftsmanship approaching art. They expected cheap materials. They found alloys America hadn't even tested. They expected conventional aerodynamic design. They found something else entirely, something revolutionary. The Zero's wing looked simple from a distance, long, gentle, beautifully curved. But when engineers began measuring, they grew confused. The curvature didn't follow Western formulas. In fact, it didn't follow any known formula. It was smooth, but not symmetrical. Evenly rounded, but varying by millimeters. Thick at the root, but thinning in a way no American textbook had ever predicted. The Zero's wing was not designed by equations. It had been sculpted. American engineers stared at it in silence. Copying this would not be easy. What America missed. This is the part of the story most documentaries skip. Most people think America failed to copy the Zero because it was lightweight. It lacked armor. It sacrificed safety for agility. Those were true, but they were not the reason America couldn't replicate its performance. The real reason was the curve. The Zero used a complex variable airfoil, a wing shape that changed subtly from root to tip. In modern terms, engineers call it a hybrid laminar profile. But that phrase hides the truth. No American factory in 1942 could mass-produce such a shape with that level of precision. The wing had to be perfect, not close, not approximate, perfect. And America couldn't build perfect wings at wartime speed. Not in 1942, not at scale, not with the available machinery. So the United States did what it always did. It built something else, something stronger, faster, more durable, but never as agile. The Zero's secret remained just out of reach. Japan's wingmaker. Behind the curve was a man few in the West ever learned about, Jiro Horikoshi, the Zero's chief designer. Horikoshi believed that a wing should flow like water, smooth, uninterrupted, continuous. He rejected Western ideas of segmented surfaces, abrupt transitions, and sharply defined airfoil switches. Instead, he experimented with seamless curvature, curves that changed by fractions of degrees, curves that blended across the entire span, curves that no American milling machine of 1941 could replicate. His philosophy came from traditional Japanese craftsmanship, the way samurai swordsmiths shaped steel with attention to micro-curvature, or how wooden bows were laminated with precision down to the grain. Horikoshi brought that thinking into aviation, and that thinking outflew the West. America tries to copy the Zero. Once the captured Zero was fully repaired and flight tested, American engineers began designing replicas, but the results were disappointing. American-built wings produced more drag, stalled earlier, couldn't maintain lift during tight turns, lost control authority at high angles, and snapped under stress. Every attempt to create a Zero copy failed, not because the engineers were incompetent, but because they were building with a different philosophy. They believed in standardization. Japan believed in mastery. They believed in mathematical purity. Japan believed in sculpted perfection. They believed a wing was a mechanical component. Japan believed a wing was a living surface. The differences were cultural, but they were also aerodynamic. The one curve that made it deadly. At last, American engineers isolated the truth. The Zero's wing had a hidden advantage. Its leading-edge curve created low-pressure vortices that allowed the aircraft to maintain lift during extreme maneuvers. In simple terms, the Zero could turn without bleeding energy. It could dip its nose without stalling. It could climb suddenly without losing stability. American fighters could not match this. Pilots described it like this. It turned like a swallow. It felt alive. It pivoted, not banked. The Zero wasn't cheating physics. It was using physics the West didn't understand yet. And America couldn't reproduce it, because the curve had to be built by hand, and American industry had no time for such delicacy. The Zero takes control of the Pacific. By early 1942, the Zero wasn't just defeating American fighters, it was defining the entire air war.
Every American pilot understood one truth. If the Zero is above you, you're dead. If the Zero is behind you, you're already dead. Its unprecedented agility turned dogfights into helpless evasions. Its massive range allowed the Japanese to appear where no fighter should be able to appear. Its climb rate let it pounce from above like a predator, but none of these advantages carried the same weight as its wing. Because that wing, that impossible curve, gave the Zero an inhuman ability to change direction, and in a dogfight, Direction is life. American pilots described fighting the Zero as fighting a shadow, a phantom, a creature unconstrained by gravity. The Zero didn't merely outturn its opponents, it outthought them. It moved where American pilots had learned no airplane could move, at angles forbidden by their own training manuals, at speeds where American wings would rip free. The Zero wrote a new rulebook, and America didn't have a single airplane prepared for it. America rewrites the playbook. As Zero reports reached Washington, panic set in, but so did determination. If America couldn't copy the Zero's wing, it would have to counter it another way. So the United States Air Forces issued a new doctrine: don't dogfight a Zero. It sounded absurd. It went against every instinct a fighter pilot possessed, but it worked. The new strategy was simple: climb high, dive fast, strike once, escape before the Zero can turn. American aircraft like the F-4F Wildcat and later the F-6F Hellcat were slower in a turn, heavier in the climb, but they were stronger in the dive. The new rule was clear: fight vertically, not horizontally. It wasn't elegant, it wasn't graceful, it wasn't romantic, but it was effective. Because no matter how perfect the Zero's wing was, no matter how flawless its curve, it could not break the laws of physics. It couldn't dive as fast as an American plane. Its structure couldn't withstand the G-forces of a screaming vertical strike. Its lightweight frame buckled under speeds the Hellcat treated as routine. America had found an answer. Not a better wing, a different war. Japan realized the Zero's fatal flaw. While the Zero dazzled the world with its agility, Japan quietly discovered something more troubling. Their miracle wing, the elegant curve that gave their fighter dominance, came at a cost no one could ignore. Because that same flawless curve required thin materials, low-strength alloys, minimal reinforcement, reduced armor, and dangerously fragile fuel tanks. A wing that perfect was also a wing that fragile, and every Zero the U.S. shot down burned like paper. Japan had built the perfect offensive machine, but a terrible defensive one. The beauty of the Zero's wing was also its curse. America builds a new generation of fighters. Once the United States understood the Zero's secrets and its weaknesses, it began building a new family of fighters designed not to copy the Zero, but to kill the Zero. The Hellcat, the Corsair, and later the Mustang were all designed with one goal: beat Japanese agility with American speed and strength. These planes weren't sculpted like the Zero, they weren't delicate, they weren't elegant, they were brutal, and they were built for mass production. Where the Zero relied on artisanal precision, American fighters relied on industrial power. Where the Zero relied on evasive maneuver, America relied on decisive firepower. Where the Zero relied on perfection, America relied on durability. Over time, the Zero's advantages faded. Japan couldn't upgrade its wing because to change that beautiful curve would mean rebuilding the entire aircraft from scratch. America had chosen innovation through replacement. Japan had chosen innovation through refinement. And war rewards quantity as much as quality. How the Zero shaped American aerodynamics. Despite America's inability to copy the Zero's wing precisely, the curve it couldn't reproduce changed American aviation permanently. Engineers studying the Akutan Zero made several breakthroughs: new understandings of low-speed lift, improved control surface blending, optimized wing route airflow, the importance of continuous curvature, the benefits of hybrid airfoil profiles. These discoveries influenced later U.S. designs, including the P-51 Mustang, refined laminar flow surfaces, the F-8F Bearcat, optimized lift distribution, and early jet fighters, transitioning from straight wings to swept curves. The Zero was a teacher, one America never intended to learn from, but did nonetheless. In a way, that one captured aircraft shaped the future of American air power.
The curve that wouldn't die. Even after the war, American engineers returned to the mystery of the Zero's wing. They studied the curvature again in the 1950s. They analyzed wind tunnel recordings in the 1960s. They re-examined vibration tests in the 1970s. They reconstructed the wing digitally in the 1990s. And every time, the answer was the same. The curve cannot be replicated with simple geometry. Because it wasn't created with geometry. It was created with intuition, craftsmanship, hands. Japan's greatest aerodynamic achievement wasn't its mathematics, it was its willingness to blend art and science. America missed that, and America missed the curve. The fall of the Zero. By 1944, the war had changed. The Zero was no longer unmatched. American fighters had grown faster, stronger, and more heavily armed. American carriers launched hundreds of planes where Japan could launch dozens. And American pilots had learned the Zero's secret. It was deadly only if you fought it on its terms. And so, the Zero, once the ghost of the Pacific, became prey. Its elegant curve, once a symbol of dominance, became a reminder of Japan's industrial limits. Japan had built a masterpiece, but America had built a machine. And machines win wars. The wing that changed two air forces. In the end, the Zero's wing left two legacies. In Japan, it symbolized a golden age of craftsmanship, a fighter built with the precision of a swordsmith. In America, it triggered an engineering revolution, a demand for better wing designs, improved aerodynamics, and new manufacturing methods. The curve America failed to copy pushed American aviation forward by decades. And though the Zero lost the war, its wing won a quiet victory. Because every modern fighter jet, from the F-14 to the F-22, owes something to the lessons learned from that captured aircraft. The final truth. So what was the curve America missed? It wasn't a single measurement, it wasn't a secret blueprint, it wasn't a mystical Japanese formula lost to time. It was something simpler. A philosophy that wings should flow like living things, not be assembled like machines. A philosophy America did not understand in 1942, but understands deeply today. The Zero was more than a fighter. It was a message that even in war, innovation can come from beauty, from elegance, from mastery. And sometimes, the smallest curve can change the course of history. But to understand why America struggled so much to replicate what seemed like a simple Japanese wing design, you have to go back to the very thing American engineers misunderstood: the purpose behind the Zero's signature curve. Most Allied analysts assumed the curve was purely aerodynamic, a trick of geometry, a sleek line drawn by some Japanese draftsman who favored aesthetic forms over structural efficiency. But the truth was far stranger. The curve was not primarily about airflow at all. It was about flex. The Zero's wings were built to bend. Not a little, a lot. American engineers designing the F-4F, F-6F, and early prototype fighters treated wings the way bridge builders treat steel beams: rigid, load-bearing, designed to resist stress. Japanese engineers took the opposite approach.
They allowed their wings to act like living muscles, twisting under high G-turns, changing their shape mid-flight. To the Allies, this looked like bad engineering. To the Japanese, it was the entire point. The Zero's wing was designed around a strange philosophy. Let the plane adapt to the air rather than forcing the air to adapt to the plane. This was completely opposite to Western design thinking of the era. Instead of denying nature, they leaned into it. When American engineers studied crashed Zero wings, they found something that didn't make sense. The spars were unusually thin, the ribs flexible, and the outer panel almost soft by comparison to American aircraft. They concluded it was a weakness: poor metallurgy, inferior material, primitive wartime shortcuts.
They were wrong. This was not primitive engineering. This was purpose-built engineering. The Zero's wing was designed to twist several degrees during hard turns, creating a temporary shape change that increased lift without increasing drag. It was a natural form of variable geometry, achieved not by hydraulics or moving parts, but by the shape, curvature, and elasticity of the wing itself. America tried to copy the curve, but America did not copy the flex. And that one missing detail made all the difference. American test pilots evaluating the early wing copies reported the same issue again and again. The plane didn't respond the way the Zero did. It handled stiffly. It refused to tighten the turn at low speed. And worst of all, it lost lift exactly when the Zero gained it. US engineers didn't understand the problem because they were trying to copy something they couldn't see. You can measure camber. You can measure angle of incidence. You can measure chord length. But you cannot measure a wing's behavior when it is hitting 6 Gs at 220 knots. The Zero's wing wasn't just a shape. It was an organism. And the United States had built a statue of an athlete, expecting it to run like the real thing. But the problem went deeper than the wing itself. It extended into everything that wing was attached to. The Zero's fuselage was built using a philosophy uncommon in Western engineering: intentional softness. Instead of making a chassis that resisted aerodynamic loads, the Zero used a chassis that distributed them, like bamboo, not steel. This gave the plane a strange characteristic. It felt alive in the air. Pilots described it as a bird that obeyed. American fighters, in comparison, felt like machines, powerful, reliable, brutal machines, but machines nonetheless. And there was one more crucial detail America misunderstood. The Japanese Zero wing didn't just flex for performance, it flexed because it had to. The Zero was extremely lightweight, too lightweight for the stresses of combat, unless the wings absorbed part of those stresses by bending with them. Without the flex, the wing would have snapped. This is why Americans never managed to replicate the Zero's maneuverability by copying its wing curve. They copied the visible solution without copying the invisible problem the solution was designed to address. As American engineers ran into dead ends, wartime urgency grew sharper. Naval pilots demanded answers. Why could the Zero outturn every American fighter at low speed? Why did its handling seem to improve exactly when American aircraft fell out of the sky? The Zero was not magic. It was simply different. The United States eventually abandoned the idea of copying the Zero's wing entirely. Instead, they developed something else, something that didn't require flex, didn't require fragility, and didn't require copying an engineering philosophy they fundamentally disagreed with. They chose brute force, more power, more armor, more survivability. And in the end,
The heavy, rigid, brutally powerful American approach defeated the delicate, flexible Japanese design philosophy. Because while the Zero's curve made it deadly, it also made it vulnerable. A plane that bends effortlessly in the air bends just as easily into flames when hit by a .5 caliber round. And America, instead of copying the Zero's wing, did something far more effective. They built a plane that didn't need to turn like the Zero. They built planes that could kill the Zero before the Zero ever had the chance to use that curve at all. And that shift in design philosophy would end Japan's aerial dominance forever.